Describe the motion, cut off the border, cut this into strips. You'll glue in just the left edge so you can fold that back for the journal entry. Okay, you can glue them in order. You can kind of glue them in as we go. So, no big deal. Okay, so we have here the stick figure guy. He's just standing there. So, physics terminology, how would we describe the motion of the stick figure man?
At rest.
At rest. Go ahead and write it down. At rest. All right, so if you're at rest, I got a question for you. What is his velocity?
0.
0. His position is not changing relative to anything. Okay? What about his acceleration?
0.
Also 0. Pretty simple, pretty straightforward, but valuable information. We will use it later. Okay? So at rest. Next. Look at this guy. Careful observation. How would you describe his motion? Any word. Okay, I got the word constant out there. I like. Not quite enough, but I like.
Motion.
In motion, okay. What is that motion? Constant what?
Velocity.
Very good. Constant velocity. Now, constant velocity. How do you know he has a constant velocity? What is it that you see that indicates we have a constant velocity going on here?
The change in position.
Okay, the change in position. Do you guys see some kind of a pattern going on there?
Yes.
What about it? Every second, that position changes the same amount. You guys see that? He goes the same distance every second. Haha. That's how you know it's a constant velocity. Now we're going to put a little note here. Moving to the right. When we talked about graphing, all right, we talked about velocity has direction. If something's moving to the right, how do we describe that?
Positive.
Very good. So this guy has a positive velocity. Okay. So let's leave him for a second. Let's go to the next one. We'll come back. All right. So our next guy. Take a careful look. How would you describe his motion? Okay, I like the answer. Faster. All right, yes, but let's go to the exact description of the motion. What is he doing? What's his motion? He's not accelerating. It's a constant velocity. And you're probably like, what the? Wait. Write it down. Constant velocity. How do we know it's a constant velocity? Okay? Every time interval, he moves the same displacement, right? Moves that same distance every time interval, right? Another indicator, if you look at both these guys, you see the stick figure guy has the same, like, shape to him, like how much he's stretching out his legs there. And he's in a running position in each one of those, right? He's moving with a constant velocity. That motion is a constant thing. Okay? Yeah? All right. Again, he is moving to the right. Right? Moving to the right. Therefore, we can describe his velocity as positive velocity. All right. Now, so far, those descriptions are exactly the same. But those motions are not exactly the same. So what is the difference between those two? And it was mentioned earlier. What's different between these two motions? They're both a constant velocity. So what's the difference? One's fast, one's slow. It's just that simple. All right, so here we go. Slow velocity for the one on top. With a slow velocity. And this one has a fast velocity. Now, how do you know this guy's slow and how do you know that guy's fast? Think about it and think about what words. How would you describe that? What is it that you observe here that you know that this one's going slower and this one's going faster?
The range.
Okay, so how far he got each second. You see this one, the guy below, did farther. This guy did a shorter distance, yes? That's how you know. All right? This one, he has a small distance. He goes a small distance each second. All right, and this one goes a large distance each second. So the major difference between these two is one's slow, one's fast. All right, now for the challenge question. Dun, 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 dun. The challenge question. What is his acceleration? Okay. So, the question, what's his acceleration? So, acceleration. What is acceleration?
Any change in speed or velocity?
Oh, a change in velocity. Okay? A change in velocity, we have acceleration. So, if he has a constant velocity, how much is his velocity changing? It's not changing. Yeah, do we get that? So if it's not changing, his acceleration is 0. Do we understand? Okay. So, this guy, if he has a constant velocity, what's his acceleration? Class, what's his acceleration?
0.
Thank you. 0. All right, now for the next two guys. The last two. So here we go. How would we describe that guy's motion? Can anybody else give me an answer? How would you describe that motion? Is he at rest?
Yes.
Well, okay, right there. But is he right there, stress right there?
No.
How would you describe that?
Constant. It's accelerating.
Okay, so that right there, that second, how would you describe his motion in that second?
Constant.
How about right there?
It's accelerating.
Speed.
Ah, so he's at rest, then he's kind of going slow, and then kind of like a medium, and then kind of like fast. You guys see that?
Yes.
So, how would we describe that in one word?
Acceleration.
Yes, accelerating.
Accelerating.
Okay, so your formula for acceleration is the final velocity minus the initial velocity divided by the time. All right, so initial velocity, final velocity. Could you describe for me his initial velocity?
0.
All right, give me words to describe it. at rest. He is at rest. All right, give me a word to describe his final velocity. Fast. So look at that. We described him as being fast, right? So right here, fast. Okay, so observation here. Draw some little brackets. If his initial velocity is at rest and his final velocity is fast, we can observe what's happening to the velocity.
Changing.
The velocity is changing. The velocity is changing, which is the definition of acceleration. Oh. All right. Now, a quick note on this one. The acceleration for this guy is positive. The acceleration for this guy is positive. All right? He has a positive acceleration. How do you know that that's a positive acceleration? What is going on that you're like, oh, well, that's a positive acceleration?
With the right.
It's not about the direction, which totally throws you like, wait a second. Going to the right, positive velocity, but that doesn't apply with acceleration. All right, when we're dealing with acceleration, the direction is not something we're paying attention to. That's not something we see in the number. All right? So, the acceleration being positive has nothing to do with what direction he's going. So, what is the reason why it's a positive acceleration? What about it? What's happening to the velocity?
Increasing.
It's increasing. It's not just changing, it's increasing. It's getting bigger and bigger and bigger, so it's going faster and faster and faster and faster and faster. Okay? Accelerating. All right. So our last little stick dude there. How would you describe his motion? Decelerating. Now, interestingly enough, deceleration and acceleration use the same formula. Final velocity minus the initial velocity over time. All right, so let's talk about his initial velocity and his final velocity. How would you describe his initial velocity? He's fast. Right there, his initial velocity. He's going fast. What about his final velocity? It's 0. He's at rest. So, fast initial velocity, fast initial velocity, 0 final velocity. So, what can we observe about the velocity? What is the velocity doing? The velocity is changing. If the velocity is changing, the object, therefore, is accelerating. But you're like, wait a second, you wrote down decelerating. Okay, so key thing there. In physics, accelerating and decelerating are pretty much the same thing. There's just one major difference. His acceleration, we would describe it as negative. And why is that a negative acceleration? Because the velocity is decreasing. All right, cool. So, this journal entry kind of summarizes everything we've talked about so far with the describing of the motion. Okay? But we are not done. This journal entry is not yet complete. But you're probably thinking, but there's no more space on the page. What do I do? Where would we put more information? The oops page. So there you go. On the oops page. Don't turn the page. Just right there. Oops page. At the top, right? Graphs. So exciting. Graphs. All right. Now, the graphs we're going to draw over here are related to the motion that's just to its right. So we're going to line this up. We're going to keep this lined up across the page. So, what I want you to do, the very, very top left corner over here on the oops page, write at rest. Okay? And then right here, wherever you have the top of the paper for this one, I want you to follow that line across, and just below it, write constant velocity. Do the same thing with the next one. All right? Find where that is, the top of that paper, run across the other page, right below it. Again, write constant velocity. If you want to clarify, this one was fast. The one above is the slow. Okay? Over here, the accelerating one, find the top of the paper. Bring it across. Right, acceleration. And then your last one, follow it across the page. Deceleration. All right, under each one of these, we are going to draw two graphs. Okay? May I highly encourage you to draw these lines as straight as possible and as perpendicular as possible, which means keep that at a 90-degree angle. Okay? It'll make the graphs easier to read. So, on the left side, you're going to draw one graph. On the right side, you're going to draw another. X, Y axis. X axis and Y axis. This is where you're going to need two colors. We are going to draw a displacement versus time graph for an object at rest. What would that graph look like? All right? So, in a displacement versus time graph, the slope tells us what? The velocity. All right? The slope is the velocity in a displacement versus time graph. So what's my velocity if you're at rest? 0. So if my velocity is 0, my slope 0. What does a 0 slope look like? Horizontal. So just draw yourself a horizontal line straight across. Next, we are going to draw a velocity versus time graph for an object at rest. Does anyone remember what the slope in a velocity versus time graph tells us? It tells us the acceleration. So, if the slope is the acceleration, and if you're at rest, your acceleration is equal to 0, what is my graph going to look like? Okay, again, it's going to be horizontal. But this one is a little bit more specific. All right? So, y-axis is velocity, right? So we got positive numbers, and they're getting smaller and smaller and smaller as we go down. Right there, what's my velocity equal to? 0. So this graph, different color, is actually on the x-axis, the time axis there. Visually, at rest, it's going to be horizontal. Right? Now, constant velocity, specifically a slow one, put a little note there, a comma. We need to clarify that this is in the positive direction. Because if it was in the negative direction, it'd make the graph look different. So we need to clarify there. We have positive direction. A displacement versus time graph for an object with a slow constant velocity in the positive direction. What is that going to look like? All right, it's got slope. Is it linear or is it curved? Linear. Is it going to be a steep slope or a not so steep slope? We're going slow, not steep. So just give it a very little bit of slope there. Velocity versus time graph. In a velocity versus time graph, what does a slow constant velocity look like? Consider this for a minute. Okay, so we said our velocity right here is 0, right? As the numbers go up, how would you describe how they're changing? They're going faster. So here we're down slow, a little bit slow, a little faster, medium, fast, super fast, right? So a slow velocity, we got to be down here somewhere close to 0. Okay? Now if it's a constant velocity, a second later the velocity is still the same. And the velocity is still the same a second later. And the velocity still doesn't change. It's not going up, it's not going down, it's not going faster, not going slower. It's just the same constant velocity. Okay? So a constant velocity in a velocity versus time graph is horizontal. Now you're like, but wait a second. At rest is horizontal. In a velocity versus time graph, he has a constant velocity of 0 if he's at rest. You can think of it that way. Okay? Constant 0 velocity. Here he's got a constant slow velocity. Okay? Yeah? Kinda? All right. Constant velocity fast. Clarify positive direction. Because in a displacement versus time graph, the direction matters. So in our displacement versus time graph, what is that graph going to look like? Steep. Is it linear or curved? Linear. Linear, steep line. Fast. All right. Velocity versus time graph. What's it going to look like in a velocity versus time graph? All right, linear, I agree. And, okay, up, up, up. Okay, linear, up, up, up. And what else? Horizontal. All right, because if the velocity down here is 0, and this is slow, and now medium, and now fast. So a fast, constant velocity is still fast, and it's still fast, not getting slower, not going faster. It's just fast, fast, fast. Constant velocity. All right. Next, let's graph acceleration on a displacement versus time graph. Notice I'm not including what direction it's going. We cannot tell what direction it's going based upon the graph with acceleration and deceleration. All right, I should clarify that. In a velocity versus time graph. All right? Okay, so here we go. Displacement versus time graph. If it's accelerating. So our guy over here started at rest, right? So at rest is kind of like that horizontal thing there going on. But then slow, he's got a little bit of slope. And then a little bit faster, a little bit more slope. A little bit faster, a little bit more slope. And then a little bit more slope. And a little bit faster, a little bit more. A little faster, a little more, steeper, 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 steeper. You get a curve. You guys remember graphing that curve on the acceleration concept practice worksheet? Curve. On a displacement versus time graph, curve means it's accelerating. Okay, so the definition of acceleration is that the velocity is changing, right? The slope in a displacement versus time graph is the velocity. Notice the slope is changing. It's going from like flat to steep, 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 steep. So the velocity, the slope is changing, the velocity is changing. We're accelerating. Okay? All right. Next, velocity versus time graph. All right. Acceleration on a velocity versus time graph. What does that look like? All right. This one, linear. He started at rest, so his velocity was 0, and then he's going a little bit faster, and then a little bit faster, and then a little bit faster, and then 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 faster. Linear positive slope. Deceleration, displacement versus time. The velocity is changing, so is this going to be linear or curved? If the velocity is changing, is my graph going to be linear or curved in a displacement versus time graph? Curved. Okay? Now, how does it curve? Well, with deceleration, he starts off going fast, right? So if he starts off fast, we have to start off with a steep slope. And then he goes a little bit slower, and then a little bit slower, and then a little bit slower, and then slower, and then slower, and then slower, and then horizontal at rest. So it curves the other direction. The last graph, velocity versus time of a decelerating object. What's it going to look like, class? Linear and negative slope. Booyah. Okay, so a few notes here. Remember, the slope in velocity versus time graphs tells us the acceleration. Positive slope, accelerating. Negative slope, decelerating. Positive acceleration, negative acceleration. Going faster and faster and faster, going slower and slower and slower. Cool? We got it? All right.